Okay, this is the last topic for momentum, and it deals with this idea of elastic and inelastic collisions and combining an analysis using momentum along with using an energy analysis. So you've probably seen the word elastic and elastic already when we've talked about collisions, and this is just going to go into more detail. So if you have a collision and the kinetic energy of the system before the collision and after the collision is the same, we call that an elastic collision. So that's given by Ke total is equal to Ke prime total. So you can think of that as conservation of kinetic energy. And that doesn't always happen. That only happens with elastic collisions. So kinetic energy is not always conserved in a collision. Quite often, a bit of kinetic energy is lost to things like thermal energy and other things. And when that happens, we say that it's an inelastic collision. And if we say the two things collide and stick together, we call that totally inelastic. So those are like three different ways to express the type of collision. Elastic, kinetic energy stays the same. Inelastic, kinetic energy changes. Completely inelastic, things stick together. And if we go back to the CART's pivot interactive activity did a couple weeks ago, we can see this. So there's this video here. So it says right here it's elastic, and you watch, we have one cart move into the other. And when we analyze that data, the momentum of the left before is 0.315, so the total is 0.315. And then afterwards, there's a little bit lost, but essentially the total momentum stays the same. It's a little bit different, it's like 3% difference. And if we actually take these values for mass and velocity, we can calculate the kinetic energy before, which is 0.0031 joules. And then the kinetic energy after is 0.0031 joules. The 0% difference, the kinetic energy stayed the same. This was an inelastic collision. Conversely, if we go to an inelastic collision, like this one,
3.9.
And we look at the analysis of that one, the momentum before was 0 when you total up. So the left glider was going 0.0456, the other one was going 0.0458, opposite direction. They add up to 0, so momentum's conserved. However, the kinetic energy was 0.0052 plus another 0.0052 for a total of 0.0104 joules before. And afterwards, they weren't moving at all, so there's no kinetic energy afterwards. The kinetic energy was not conserved. So that was an inelastic collision. And in fact, we could say it's totally inelastic because they stick together. Okay, so that's the definition of elastic and inelastic. Then the next question would be, how do we use this for problem solving? So here's an example type problem. A block is sliding along a frictionless surface at 5 meters per second. And it collides into a 4 kilogram block. The blocks collide inelastically, and then the blocks slide up a frictionless ramp. How high up does the ramp go? And then another question is, how much kinetic energy is lost during the collision? So this is like a two-step problem. There's a collision problem. So in here, we analyze this with a collision. Oops. And here we do an energy analysis. So first of all, we can use momentum to analyze the collision, and then we can use energy to figure out what happens afterwards. So I can go through this. So first thing we'll do is look at the collision first. So let's do a different color because I can. Collision. So we'll do collision. And we'll do conservation of momentum. So momentum before is equal to momentum after. And so this is MAVA because this thing's not moving. So before the momentum is MAVA, and then afterwards it's them moving together. So it's MA plus MB times some V prime. So I'm going to divide both sides of the equation by this MA plus MB. So it's MA oops, VA divided by MA plus MB, that's equal to V prime. So V prime is 2.5 times 5 meters per second divided by 2.5 plus 4 kilogram block. So let's put that in my calculator here. 2.5 times 5 and then 6.5. So I get a 1.923 meters per second. So I now know how fast this thing is traveling after the collision. And we want to know how high up the ramp goes, and that's a conservation of energy thing. So if we say this is our zero baseline for gravity, so in other words there's no gravitational energy at this level, then on this side before it goes up the ramp there's some kinetic energy, and then afterwards at its highest point it's not moving anymore, so there's no more kinetic energy, but it all turns or transfers to gravitational energy. And it's frictionless. We're going to say there's no thermal energy loss. So we're just going to say EK equals EG. So EG is equal to EK, which is 1/2 MA plus MB. They're the two masses combined times V prime squared. So that's 1/2 2.5 plus 4 times 1.923 squared. So that is, there's my screen, 6.5 divided by 2, and then it's this other number squared, multiply, I get 12.019 joules. Okay, so we know how much gravitational energy is at that final thing. So now we want to go mgh equals 12.019. So H equals 12.019 divided by 9.8 divided by their mass, 2.5 plus 4. Over that, 6.5. So it's going to go up 0.188 meters. Okay. And how much kinetic energy is lost during the collision? Well, that's a good question. We know the kinetic energy after the collision is this 12.019 joules. Let's find out how much kinetic energy there was before the collision. So EK. There's no EKB, it was not moving, so we only have to figure out the kinetic energy of mass A. So that's 1/2 MA VA squared. So 1/2 2.5 5 squared. So that's 2.5. That's 1.25. Whatever. 25. So 31. Oof. Joules. And so we have a lot of energy loss actually. E loss is equal to EK minus EK prime. So 31.25 minus 12.019. That was, so it lost like 19 joules of energy during the collision. So a lot of vibration, essentially. So once again, the collision is a momentum question. Before or afterwards, it could be an energy analysis. So we solve collisions using conservation of momentum. And then we can analyze objects before or after the collision using conservation of energy. Only if we're certain that the collision is elastic can we use conservation of energy to analyze the collision. So here's another kind of sample problem. So a ball of mass is moving east, collides with a ball moving west. After the collision, the ball has a new speed. Is this collision elastic or inelastic? So at this point, I'd say we don't know. We know that we have, I'm going to call this M1, we'll call this one M2. So we have M1 going this way, 3.5, and we have M2. We have a dog barking. It's my dog. We have M2 going that way at 2 meters per second, and then they collide. So afterwards, we have M1 is still moving east, but slower. And I guess M2 better be moving east as well. But we don't know what that speed is. And because we don't know the speed, we don't know if it's elastic or not. So we have to use conservation of momentum to figure out this velocity. So we have M1 is 3.5 meters per second. Oops, that's V1. M1 is 0.2 kilograms. V1 prime is 0.5 meters per second. M2 is 0.3 kilograms. V2 is negative 2.0 meters per second, and we're looking for V2 prime. You know what? I think I'm going to change this question just a little bit, just to make sure it works out okay. I'm going to change this to 0.10 meters per second. Okay, so total momentum before has to be equal to total momentum afterwards. So the total momentum before is M1 V1 plus M2 V2, and afterwards it's M1 V1 prime plus M2 V2 prime. And I know everything but the V2 prime, so we can solve for that. So it'll be, first I'll subtract this one for both sides, so I'll get on that side of the equation. So M1 V1 minus M1 V1 prime plus M2 V2 equals M2 V2 prime. And then I'll just divide both sides by M2. That cancels that out. So I get V2 prime equals, now I'll plug my numbers in here. So M1 is 0.2, 3.5 minus 0.2 minus 0.1, and then plus 0.3, and then the V2 is a negative 2. All that is over 0.3. Okay, so what I'll do is put that in my calculator here. So I got 0.2, 3.5, 0.2, 0.1, subtract that, 0.3, 2, subtract that, so I get 0.08 divided by 0.3. So I get 0.2666. So that's going in east. So that's good. This one's going east as well. It's slower than that. That doesn't quite make sense. Oh no, this is actually, sorry, this is 0.1. Does that make sense? That's fine. Okay, so we now know this velocity. So now we can check to see if it's collisions elastic or inelastic. So let's do that here. Let's use a different color. So EK before is equal to 1/2 M1 V1 squared plus 1/2 M2 V2 squared. 0.2, 3.5 squared plus 1/2 0.3, 2 squared. Okay, let's punch these numbers in here. 0.1 times 3.5 squared times 0.3 divided by 2, 4. Add those. I got 1.825 joules. And then afterwards, it's 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. That was 0.1 squared plus 1/2 0.3 0.2667 squared 0.1 squared. That's that one. 0.3 divided by 2. 0.2667 squared times, add them together, 0.0117. 0.00117. There you go. Definitely inelastic, no question. So we could have never used kinetic energy to solve for that V. It would never have worked out properly. Okay, last example. I won't do the full example, but I'll show you how it kind of works. This is a real life example then. This is how they do ballistics testing. This is how they test, or one way they test how fast bullets fire from guns. And what they do is, they'll have like a gun here, some kind of gun. And the gun will shoot a bullet, and the bullet's gonna hit this blob. It's gonna be something that allows the bullet to go into it, like a heavy piece of cork or something, maybe like a heavy piece of wood actually. And that wood is hanging off a ceiling using some kind of cable or wire. And then once the bullet is embedded into that wood, it swings up kind of like a pendulum. It goes up like this. And this is another one of those combination analysis. First you analyze this collision using momentum, and then you use conservation of energy to figure out the height. Actually, they actually do it backwards. What they do is they'll analyze this pendulum swing, the swinging of this mass, and then since they know that the height that it comes up, they'll know the gravitational energy, which means that they'll know the kinetic energy. And once they know the kinetic energy, they can get the velocity. And then once they know the velocity, they can work backwards through the collision. So it's almost exactly like this problem, only that they go backwards. They start here and go this way through the problem. Other than that, it's pretty much exactly the same. The last thing that's kind of tricky about these problems is there's a little bit of geometry. They'll probably measure the angle of the swing, and then you have to use a bit of trigonometry to get this height h. And if you have a good drawing, it's kind of easy to see. If I draw this triangle here, so this is the length of the wire, this is the angle, so we can calculate this length there, and then from this point to this point is that starting length of the wire. So if you know this, and you know, if you know that, you know that, you can figure out the height. Once you know the height, you can get the gravitational energy, then you get the kinetic energy, then you do momentum to work backwards to the starting velocity. Okay, so that is the quick tutorial on using momentum and kinetic energy together.